next talk will be on the Flambda2 Validator by Irene Yoon.
OK, cool, thanks. Today I'll talk about our work on the Flambda2 Validator. I'm Irene Yoon, a postdoc at Inria, and this is joint work with Chris at Jane Street. So quick primer about the Flambda optimization pass. So the Flambda optimization pass is a pass in the middle end of the OCaml compiler, as many of you probably are already familiar. And one of its main features is for inlining function calls. So for example, if you have this simple factorial function, and if you have let n that applies 4 to the factorial, then it can inline the function call to factorial so that you can do some compile time reduction of terms, so that at the end, let n can be just reduced to 4 times factorial 3 instead of having the whole body of the factorial function. So the Flambda optimization, there was a sort of Flambda1, the original optimization pass. And behind the scenes, it had an ANF-like representation. And it also had a lot of internal representation. So ANF is this form where you have a series of let bindings in a certain normal form. And this IR has several characteristics, such as it's not necessarily preserved under function inlining. For instance, if you were to just imagine in this small code snippet, G containing some let bindings, and if you were to inline that in the below snippet, you would see that it's no longer in normal form because you have nested let bindings. And typically, you have to do this sort of join point rewriting, where you have to rewrite in order for your term to be in normalization, which could be inefficient. And certain control flow optimizations are also difficult to reason about. So Flambda2 is ongoing development that is for better inlining for the OCaml middle end. And unlike Flambda1, it is a sort of CPS-based transformation inspired by compiling with continuations continued, suggested by a publication by Andrew Kennedy in 2007. And in terms of the compiler, it sits in the same location as the Flambda pass, where it takes it in Lambda terms, and it targets a new IR called Flambda2, and it emits CMM terms. So in terms of the design choices that can be made at this level of the IR, it's actually not so straightforward what kind of IR you might want to have and what kind of optimization you might want to have. This is actually a research question that many people have been thinking about. Oh, the animation here is. So classically, there's about like 3 choices that you can make at this level of the compiler in terms of IR. Many known things, these are classic ideas that has been researched for decades at this point, is forms such as SSA, where each variable has only one definition site, which is good for data flow analysis used for IR such as LLVM IR. There is also commonly used continuation passing style, a variant of lambda calculus where functions do not return but apply a continuation to their result. And one nicety of continuation passing style, for instance, is full beta reduction is sound in the sense that if you see these 2 snippets, you can see that for the left-hand side expression, if you were to apply lambda x dot 0 to f of y, if f of y, if f were to be non-terminating or were to have side effects, and you wanted to do full reduction here, it would be unsound because in the case that f were to indeed have some side effects, you would be throwing away that side effect. Whereas if this term were to be in CPS form, you wouldn't be throwing away the side effect. So this is one reason why you might want your IR to be in CPS style if you care about function inlining. And as I've hinted at earlier, ANF is a variant with flat let bindings, which requires commuting conversion, which can be inefficient. And in fact, there has been other works by various people that discusses the whether or not we need to choose one decision over another and the advantages and disadvantages over the other. So our contribution specifically is about Flambda2, which makes some interesting design decisions in this domain. So our contribution is a validator for Flambda2. So the Flambda2 pass is under active development. Currently, it's around 95,000 lines of code. And it combines various ideas from this domain where the IR itself is a mix of CPS, ANF, and direct style. And it uses data flow analysis to do some pretty advanced optimizations in one pass where it does both CSC, it does speculative inlining, unbossing, value tracking, and match, and that's just several of the features that is covered with Flambda2. So our goal in implementing this validator is we wanted to see whether or not it was possible to write a declarative specification for the reduction behavior of Flambda2 to better understand what this optimization path is doing, and whether or not we can validate its outputs in a relatively simple manner. So how do we do this? So we took a pretty classic approach. We tried to do translation validation. So this is a way of checking a posteriori the correctness of a run of compilation versus compare this to compiler verification, which shows the correctness of a compilation pass. So this was also inspired by several similar approaches, such as validating register allocation and spilling by Rideau and Leroy in 2010, and semantic equivalence checking for HHVM bytecode by Nick Benton in 2018. So what we do at the high level is we do some semantic equivalence checking of Flambda terms. So this is the Flambda2 optimization pass. So the Flambda2 IR has a simplification pass which goes from the IR to the IR itself, and it does several. It does a simplification step which implements several optimizations at once, which I mentioned, such as match, function inlining, and CSE. And in order to validate this, we actually define a translation to what we call an Flambda2 core term, which is a new IR that we defined in this validator, which is a more lambda calculus-like view to the IR. And then we defined a normalization scheme for this Flambda2 core term so that these translated terms, we can check for its alpha equivalence. So if the translated and normalized terms are alpha equivalent, we say that they're validated. If not, we don't guarantee any results about the input and outputs of the Flambda2 optimization. So with a validate flag, given a source ML program and a single run of the optimization, we can show the semantic equivalence between the input and output using our scheme. So I want to also explain what was the kind of the core features of this Flambda2 core terms versus Flambda2 without going too much into detail. So Flambda2 core, we thought about it kind of having the lambda calculus hat on and seeing Flambda2 in a little bit more of a simpler way. One core difference between Flambda2 core and Flambda2, of course, is when you want to do function inlining, you typically don't want to do full sub-expression inlining because oftentimes that results in much more inefficient terms. But for the sake of validating our terms, actually being able to do having full sub-expression in argument position is okay, as long as we're okay with term explosion. So Flambda2 core allows for full sub-expressions in argument position so that there can be more aggressive inlining in the normalization process. It's more like the lambda calculus in that there's more uniform representations of lambda terms. We have uniform closure bindings. So there are closure bindings in Flambda2, which represents non-recursive and recursive closures. And we have unified these closure bindings so that we have a simpler normalization process. And as I've said, the translation scheme unifies all lambda-like constructs to use this same closure binding, and this makes the treatment of recursive terms a bit simpler. And Next, I'll talk also a little bit high level about what we do with normalization. So without going into too much detail, the normalization, there is kind of a tension here where we want to normalize, but we cannot fully reduce at all times because inevitably it will not terminate if we continue to try to normalize and try to inline recursive terms. We don't know whether or not that will terminate. So our approach was that we try to define as simple of an operational semantics to this data flow-based optimization as possible. And one disadvantage that we do have is that termination is not guaranteed under our normalization scheme. We have no proof of termination for our normalization. And the size of the terms, although we have tried to keep it as small as possible, they tend to be quite big because we allow for full sub-expressions and arguments. So the set of operational semantics that we've defined through experimental observations on Flambda2, and there's rules around non-recursive, recursive, and local continuation so that we ensure certain normal forms for recursive closures so that we can still do interesting optimizations such as being able to do argument elimination in case an argument for a recursive call happens to be invariant. Another interesting thing is that we still also do, although it's not shown in the rules here, we also do in the process some very simple static analysis, which is needed for checking some recursive terms and preventing further term explosion. So in terms of results, the test suite was the OCaml standard library for Flambda2 of the OCaml compiler. We tested it on the AMD EPIC 7002 processor with time limit of 20 minutes per file. And for the standard library, out of 67 files, we were able to validate 45 files. And 14 files we did not validate, and 8 files timeout. And the validator itself is around 7,000 lines of code, whereas the Flambda pass is 95,000 lines of code. So at the end, it is less than 10% of the size of Flambda2. So we were happy that the validator is still relatively small relative to the pass. So modulo the limitation that will be discussed in a couple slides. And a note about performance. The performance itself is bimodal. So out of the 59 files that do not complete and do not time out, 43 completed under a second. So this chart is saying all the files that did not time out. And then this is seconds, and then the cap is around 20 minutes. And only 5 required more than a minute in this case. And from our observation, the speed did not seem to strongly correlate with the program size, and we still need to do some further investigation on why these specific files time out. So, of course, there are still some limitations on this work. Results show partial success, but we also encountered some optimizations that are challenging to validate with this specific technique, such as cross-module inlining, which is a useful optimization, and it's not a theoretical obstacle, but for the performance of the validator, the term size would explode already. The term sizes get quite large testing without cross-module inlining. Nuanced approach would replicate Flambda2's cross-module inlining decisions because Flambda2 does have inlining tree that reports when it will inline or not. And another subtlety is function argument introduction and elimination. So Flambda2 does some fancier static analysis on when a certain argument is invariant over recursive functions, and we do not have such a static analysis pass. We only have a very simple way of detecting it, so this is also for future work. And the current development is available up in the link above. Thank you.
Thanks, and we've plenty of time for questions.
The ones that didn't validate, is it was it because the validator is not complete, or is it because you actually found errors in the optimizations? You had some that didn't validate, as something like 14% something.
Right. The parts that did not validate was partially because of it was the limitations that we've discussed here, because we weren't able to. Some of the simplification done by the Flambda2 compiler for the standard library was using cross-module inlining, and it wouldn't, or function argument introduction and elimination, and it wouldn't validate because we didn't support these yet. Yes?
Hi. This is great. The Flambda1 pass output a sort of script that it sort of says what it did, sort of. Does Flambda2 does that? And if it did, would it help you, guide the explosion a little bit to do the validation?
Right, so I'm not too familiar with Flambda1, but Flambda2, perhaps you're talking about sort of the inlining decision tree.
Yeah.
Yes, Flambda2 does have that as well, and if we were to use that, perhaps we'll prevent more term explosion. Yeah.
Okay.
Thank you.
Thanks for the talk. So I'm curious now, which find the timeout in the OCaml standard library? I imagine probably Caml internal format things?
Yes. It cut off, but it's there. I think that's, yeah.
So there is one Caml internal file that doesn't time out and the other does, something like that?
Yes, for some reason.
Oh,
Thank you.
Thanks for the talk. So you introduced a new IR because it would make your life easier to write this validator. You also think that it would have helped write Flambda2 in retrospect by choosing this new IR instead of the current IR that's used?
It could have helped, but there are practical necessities that exist in Flambda2 that we could safely ignore in Flambda2 core. So there are several things, such as there's more identifiers in Flambda2 because certain identifiers, like the memory representation, is actually important for efficiency reasons. So I think the part that could have helped is perhaps the uniform representation of closures could have helped. But otherwise, there are practical details in Flambda2 itself that do need to exist there. So I think perhaps the closure representation and the identifiers, I think, could have helped in the design itself. But right, there's still a lot of complications in Flambda2 IR.
Thank you.
Yeah. Mm-hmm.
Did you find incorrect optimizations when running your validator?
No, we did not find any incorrect optimizations using the validator. That's for, hopefully, if this becomes more robust, we'll find some.
Could you try it with a buggy version of the optimizer? See how good it is?
Sorry?
Could you try it with a version of the optimizer that you know has a bug and see how well this catches it?
Yes, we have not tried this. We could, yes.
Okay, let's thank the speaker again.
Thank you.